Hello, it's Richard Chesterwood here with a short video where I'm going to address the biggest question that I've had since I released my Deploying Microservices course. And that question was, how do we secure the microservices? Now I have on screen here the system up and running exactly as it was at the end of that Deploying Microservices course. And I realise that some of you watching this video might not have done that course. If you haven't, then I strongly recommend it. It's a hard course, but there's a lot of really valuable information in there. So a very quick overview if you haven't done that course before. Although what we're seeing here is a regular web application developed in Spring Boot, behind this web application is a large collection, and I'm here in my Amazon Web Services console. I think it's about 9 separate instances, most of which are very small T2 nano instances. And each of these instances are running some kind of a microservice. One of the instances here is the web server itself. And the microservice of real interest on the previous course was the position tracker microservice. So anyway, do check out that course if you want to know more. But as I said, one of the most common questions that I had from viewers of that course was, how do we secure the architecture? Now, what we don't mean by that question is, how would we secure this web application from a user's point of view? That's really a trivial thing to do because the web app is just a regular Spring Boot application. And therefore, for this web app, we could very easily apply Spring Security and we would build login screens and so on as usual. We have a full suite of Spring Security courses at virtualpairprogrammers.com. We have a module covering the core concepts. And actually, you probably find all you need in there. Using Spring Security, you can set up form or basic authentication to secure a web app. So that's boring, but the real question is, how do we secure the actual web services themselves? So at the moment, we have every single microservice being deployed to a T2 nano instance, such as the position tracker here. And you can see here in the console that it has a public IP address, this 54.154.11.71, and this is the heart of the problem. This IP address is, of course, visible to the entire world. So if a hacker, or, well, anyone really, but let's think in terms of hackers, if they could somehow guess this IP address, and they could guess the port that the microservice is running on, then they could access that microservice directly. Well, I did that in a browser a few moments ago, so there's the IP address I just showed you. The port that this microservice runs on is a REST service running on port 8080. And something else that the hacker would have to guess is that we have a URL pattern or a URI pattern assigned to each resource in this REST system. So if we have /vehicles/city truck, well, you can see that this is responding, and it's responding with an XML document. Now, clearly, this is not supposed to be a public-facing microservice, and members of the public should not be able to access this URL. Well, okay, for this system, the data that we're leaking here, this position of latitude and longitude and a timestamp, probably isn't that important. But of course, in your system, this could be sensitive data like credit card numbers, medical information, or whatever. And it really is a disaster that we've exposed this data to the public. Now, you might be thinking, well, who cares? What are the chances that a hacker could have guessed this IP address and the port and the URL pattern? So you might be thinking that, oh, well, there's no need to bother securing this microservice because nobody's ever going to find it. Well, if you are thinking that, then what you're relying on there is something called security through obscurity. And you should absolutely go away and read this Wikipedia page, at least as a starting point. And let's be clear that you should never rely on security through obscurity. For one thing, hackers are always cleverer than you think they are, and they'll find a way. They'll use IP address scanners, port scanners, and there's always the possibility on big projects at least that some malicious insider on your project might leak that information to external hackers. So the upshot of this is we absolutely do need to secure this microservice. Well, do you know, I could just wave my hands here and use exactly the same arguments I used before. This microservice is itself a regular Spring Boot app. I could go into that Spring Boot app and quite easily add some basic authentication to the application, and I'd set up a username and password. And then even if a hacker did find the IP address, port number, and URL pattern, well, they would be locked out as long as they don't know the username and password. Now that would work, but of course that would now mean that every single genuine client of the microservice would have to be coded so that they are going to send the username and password. Here's a simplified architecture diagram of the system. And the one big client that we have so far for the position tracking system is the web front end itself. So I hope it's obvious that if we put basic authentication onto the position tracker, then we'd have to make sure that any call that we make from this web front end, this REST call here, would have to send the username and password. We'd probably also need to use SSL for that connection as well. Now, again, that's not hard to do. On the second module of Spring Security, this is the one where we looked at REST. Just going down to chapter 2 on there, I showed you how to secure a REST web service, which, as the comment here says, it's really just a case of applying standard Spring Security. On the client side, you have to send the username and password in base64 encoded format. A little tricky, but really quite simple to do. So we could certainly do that, but I think on a full system that's going to end up being very tedious and very painful because, remember, I know I've said this a lot on the previous course, we only have one real microservice on this architecture now, but the intention is this would scale up, and as we add more and more features, we're going to get lots more microservices. So it's common to have hundreds or even thousands of microservices on a real architecture. Now, that to me sounds like a hideous amount of work to set up basic authentication on every single microservice. We'd also have issues such as how do we manage those usernames and passwords? If we decide, for example, that we're going to rotate the usernames and passwords every month, which sounds like a sensible thing to do, then we'd have to think about how to have a mechanism to handle that. We'd have to automatically change the clients and the services. And, well, I don't know, really, that sounds like a lot of work. There are some software solutions to this which use a kind of OAuth style system of maintaining a token repository. And then basically all of the clients in your system acquire tokens from that token repository. That sounds like a good way of working, but I have to confess that I have never used such a system because I'm going to be showing you a pretty simple way of acquiring security for this system, but actually a very powerful way as well. I don't want you to think that because what I'm about to show you here is simple, that it's somehow not very good. In fact, in security, often the simpler solutions are better. If you have a complex solution, then it's more likely that you're going to implement it incorrectly or something is going to break later on down the line. If you stick to something simple and it's easier to work with, then you're more likely to use it properly. And as long as the solution you're using is robust, then it doesn't matter if it's simple. So you might have guessed what the solution is going to be from the title of this video. We are going to use the power of Amazon's virtual private cloud. I talked a little bit about this on the microservice deployment course, and we came across the virtual private cloud a couple of times, in particular when we needed to deploy our microservices to multiple availability zones. But one feature that we didn't exploit was the private part of a virtual private cloud. Let me give a very basic recap of how the Amazon Virtual Private Cloud works. Within your Amazon Web Services account, you can create multiple virtual private clouds. And in general, what you'll probably be doing is creating one virtual private cloud for each of your systems. Now, I'm being a little bit vague there. There's actually lots of different ways of dicing and slicing this, but that's the obvious use of a virtual private cloud. We, in our example, would have one virtual private cloud containing the Fleetman system and nothing else. And you'll recall from a virtual private cloud, when we launch an instance into the virtual private cloud, we have a choice. We can either make the instance be private or public. And very simply, the difference between the two is that a public instance in your virtual private cloud will be allocated a public-facing IP address, a regular IP address, whereas a private instance will not get a public IP address, and therefore it can't be accessed from anywhere outside the VPC. And this is the solution that I'm proposing. Of course, our web server, our web application will have a public IP address, but for all of our microservices, we can simply ensure that the microservices are not given a public IP address. If they don't have a public IP address, then they can't be contacted from anywhere in the outside world, and they become internal to this system. Now, I realise that won't satisfy all requirements. I can imagine that there will be some systems that you're building where you have a microservice, like this one here, and yes, it's going to be used internally by other microservices and a web application possibly, but you might have a requirement that you do have to expose that to some remote clients outside of the virtual private cloud, in which case, then yes, you would have to look at implementing a regular authentication method on that instance. But if you're in the very common situation where these instances are completely private, they're only going to be used by this application, then this is the way to go. Just make them private in your VPC. I'll show you how to apply this to your existing architecture in a short while, but before I do that, I thought I'd just show you how you can launch a private instance straight into your VPC. And we'll do this manually in the AWS console. So a regular launch instance, and we're going for the Amazon Linux AMI, and we'll go for the T2 Nano, keep costs down. And it's this step here, step 3, which is the crucial step. We have one instance, and it's asking which network do we want to deploy this to. Now, what this is really saying is which VPC are we launching the instance into? Now, in this account, I've only created one VPC. In fact, it's the one that you get by default. Most of you watching this video will have had a VPC created for free. There are some edge cases. If you created your Amazon account before 2009, and that's when Amazon introduced VPCs, then you might have an old style of network called EC2 Classic. And that just meant no VPC. And really, for legacy reasons, if you've got an old account, you might see on this drop down a reference to EC2 Classic. We talked a bit about subnets on the previous course, and the default option here is that it will pick a random subnet to launch into. But if I want to, I can be explicit. I can insist that this gets launched in zone B of my region. But now here's the interesting field, auto assign public IP. Now the default for this is to use whatever setting we've set for the subnet. Now I can show you this in a few moments, but when you create these subnets, and again, if you're working on a fresh account, your subnets will have been automatically created, but you can manually create subnets as well. Part of the settings for the subnet is, are we going to default to public or private instances when new instances are created? And the default was public. So that's what it's saying here. The subnet setting is to enable public IP addresses. Well, I can very simply switch that to disable. And that's all I really need to do. I can now go through all of the remaining steps. I may as well add a tag onto this. I'll just call this VPC test so I don't get it confused with everything else. Now for the security group, and I'll return to this shortly, but for now I'm going to create a new security group which just has SSH enabled, port 22, and I'm going to go with this default setting, which is the wide open setting. This is saying that anybody, anywhere in the world on any IP address can access port 22 on this instance. Now I don't want that to confuse you. Remember that I'm going to launch this instance with no public IP address. So in a way, this security firewall setting is irrelevant because no instances outside the virtual private cloud are going to be able to see the instance anyway. I will come back to that security group, but for now, the settings on here aren't so important. And I'm going to reuse the key pair that I was using on the previous course. If you're doing this and you haven't done the course, then of course you will have to generate yourself a key pair file. Let's launch that instance. Well, that took a few moments to launch as usual, and here it is in the console. And I hope you can see now that the big difference is that although there is a private IP address here beginning 172, there is nothing appearing under the public DNS or the public IP field. So it simply doesn't have a public IP address. So what that means is, here I have a terminal. This is on my local development machine. And even if I try to SSH in with the correct key pair, and I think I demonstrated this on the previous course, the IP address here beginning 172 is not going to work because it simply isn't a public IP address. And I can wait as long as I like on there. It will eventually time out, of course. And this IP address would only work if there was a piece of hardware on my local private network in the studio that I'm working in right now with that address. I mentioned this on the previous course as well, that you can always identify a private IP address because they are defined by the Internet Protocol. You can check out the Wikipedia page called Private Network, and there are 3 different types of private IP address. All IP addresses beginning with 10 are private. There's a block of about 1 million addresses beginning 172, followed by anything from 16 to 31. They're all private. So yeah, we had a 31 there, so definitely private. There's 65,000 addresses beginning 192.168. Now, of course, we do need some way of accessing this instance so that we can do work on it. And the way that you do that is connecting to one of your public instances. As long as the public instance is a member of the virtual private cloud, then it will be able to see all of the private instances. Remember that we have an instance for our Ansible controller. So that one does have a public IP address, this one beginning 54. So if I try to SSH into the Ansible controller, no problem there. I am now inside my virtual private cloud. So from here, and just as on the course, we do have that key pair uploaded to here. So from here, I can do SSH using that key pair file. And this will be EC2 user at, and I'll remind myself now of the private IP address of my new test instance, 172.31.32.20. And that's looking good. Confirm that I want to connect, and I'm now into that private instance. So that's great. And if we can make things now so that we can get our microservice running on this private instance, then we have what we need. Nobody from the outside world would be able to connect to it. So at first then, it looks like that all we need to do is make sure that when the position tracker microservice is launched, and we're doing that using an Ansible script, we need to make sure that the setting for that new instance is that it does not acquire a public IP address. Well, it is going to be more complicated than that, which is why I decided to split this into a little course on its own. But let's at least try it and let's see why it doesn't quite work. First of all, we don't need this VPC test anymore, so I will terminate that. And in fact, I'm actually going to terminate the position tracker as well, because I'm going to change the Ansible script that we're using to launch it. It is quite a complicated system, this, but remember that the way that we're launching the position tracker is via Jenkins. We have a project inside Jenkins for the position tracker, and Jenkins is triggering the deployment using a deployment pipeline. And that deployment pipeline is configured using a script inside the repository for this microservice. And as on the previous course, you should have a GitHub repository that you've forked from my repository containing your Fleetman position tracker. Now, if you're watching this video standalone and you're not doing the full course, then all I'm saying is here you would need to get access to your Ansible script, your deployment script. Now, we have that in the root of our project. It's called deploy.yaml. Now, if we go down to the task here, the EC2 task, this is the task that's launching the instance. Now, if you remember that on the console a few moments ago, when we launched the instance, we just had to change a switch to disable public IP address. You might think, therefore, that we just need to add in a field here. And that does look correct. Here on the Ansible docs for the EC2 task, in fact, it's the first option in the list, assign public IP, and we can choose yes or no. But as I say, it is going to be more complicated than this. It looks like all we have to do is set this parameter to no. Well, let's try it then. So in your deploy.yaml script, we'll add that in. So it's on the EC2 task, and it's assign underscore public underscore IP. And we'll try setting that to no. Okay, good. I'll add in the commit comments here, trying to stop public IP assignment. So I've committed the changes. I haven't set up the auto triggering of builds on this particular environment, so I'll need to go in here and manually run that build. As always, that'll take a while. So I'm now monitoring the console for this build. We've got to the stage where it's provisioning an instance, so this is actually the crucial step, and it looked like that went through okay, and it did. It's waiting for the server to start responding, but actually we can now go across to the Amazon EC2 console and do a refresh and see what's happening. So here is my new position tracker. It's currently in the initializing state, but this is very disappointing. Can you see there that it does still have a public IP address? Not what we'd expected. So that is disappointing. And when I first came across this, I was very confused and spent quite a lot of time trying to find out what the root of the problem is. I think it's actually possibly a quirk of Ansible that isn't very well documented here. But it turns out that it doesn't matter what you say in this assign public IP field if the subnet that we're launching into is set to enable public IP addresses. Now, to explain that, looking back to the script, our deploy script, the deploy.yaml file, you'll notice that I'm not actually specifying anywhere in here which subnet I want the instance to be launched into. So it appears to be choosing a random subnet to launch this position tracker into, which happens to be the subnet that we have for Zone C. Now, I know I haven't talked a lot about subnets on the previous course, so I think it would be worthwhile, for the first time, going into a little detail on that. So clearly this position tracker is not working, so I'm going to terminate that to get it out of the way. And to have a look at the details of our subnets, you need to switch services. So on the Services tab, you'll find all of this under the VPC service, under Networking and Content Delivery. We have on this page a link to our VPCs. Now, because we've never bothered creating one, we just have the default VPC, but that is effectively the Fleetman VPC. We could go ahead and create more VPCs for other systems. But then we have a link to the subnets for our VPC. Now, I did talk in some detail about subnets on the previous course. I've told you that subnets serve two purposes that we're aware of. First of all, a subnet is a range of IP addresses. And by default in this region, you might see different in different regions, but in this region, we've had 3 subnets created automatically. And each of those subnets is relating to a different availability zone. In other words, a different data center, physically separate data center. And we were using these subnets on the previous course to make sure that, for example, our registry service called Eureka, we have 2 copies of that deployed to different availability zones. That's good for redundancy. But what we also have in a subnet is a range of IP addresses for that subnet. And that's configured in this column here. Now, what I didn't talk about at all was the concept of CIDR. Now, this is slightly complicated. It stands for Classless Inter-Domain Routing. But really, that's a fancy way of saying this is a way of defining a range of IP addresses. So let's go with this one here. This is the one for Zone C. What this is saying is that we have a range of addresses starting from 172.31.0.0. And the /20 is saying how many addresses are going to be in this block. So there will also in this block be address 172.31.0.1, .0.2, .0.3, and so on. And actually it's telling you in this column here that there are going to be 4,087 addresses in this block. Now it is quite difficult to work out just by looking at the CIDR, how many addresses there are and exactly how this /20 works. In fact, it works via a bitmask. And it's saying here that there are 20 bits in that bitmask. Now, as I'm not a network expert and this course is not strictly a course on networking, I'm not going to do a full explanation of how that bitmask works. But what I would recommend you do if you're new to this is there's lots of resources online. I just have a random one here which will calculate IP ranges for you. So if we take this here, the one ending in /20, and paste it into there and click calculate, it will tell us what the first IP address in this block is, 172.31.0.0, and it will tell us what the last IP in this block is. And it turns out to be 172.31.15.255. So in other words, what this Amazon default is it's given us all of the IP addresses beginning 172.31. And then anything from 0 to 15, and then anything on the final number. And that gives us 4,096 addresses. And if you want to learn more, you can play around with this mask. For example, a /32 on the end will give you precisely 1 address, or a /16 will give you 65,536 addresses. Do have a play around with that if you want to learn more. So you'll see why that's useful in a few moments. But the relevant thing for us is that if I select any of these subnets, you'll see that the setting here is auto assign public IP, and that has been set to yes by default. And unfortunately, for some reason that I don't fully understand, our Ansible script cannot override that default. What I could do is take each of these subnets, and it's actually quite a simple task to select modify auto assign IP settings, and I could disable it and then click on save. Well, I'm not going to do that because the problem then is that all of the instances that we launch are going to end up being private, and that's going to affect instances such as our Eureka server and, of course, our public-facing web page. A very common approach here, instead, is to be a little more structured in the way that we work with subnets. And what we're going to do is we're going to define separate private and public subnets. And that's very easy to do. We can create as many of these subnets as we like. So on this diagram here, it's just an example. As an architect, we might decide that we want a subnet for each of our availability zones. We're going to make these subnets be private. We're going to create a further subnet here, which is also for zone A, but we'll make this subnet be public. So any instances launched into here will by default be public. Any instances launched into here will by default be private. And I can do any combination that I like in here. I could create further public subnets for the other availability zones as well. Now what we have here, although we didn't create it, the default we've been given here is a subnet for each availability zone set to public. So I'm going to suggest that we go in for each of them and give them a label. And you can do that just by clicking on the name here. So this is a subnet for zone 1B and it's public. So let's make that clear by changing its name to public_B. And then this one will be public_A. And this one will be public_C. So these are the subnets we've been using so far. But what we want now is a new subnet, which is going to be private, and we're going to launch our microservice into it. So we can create a new subnet, no problem at all. So the name of this one will be private. I'm going to make this be the private subnet for zone A. So we need to specify which VPC it's part of. Well, we've only got one. The availability zone, that will be easy. That's going to be zone A. But now the difficult bit, we need to specify which range of IP addresses is this subnet going to use. It is entirely up to you how you allocate these IP addresses. They're all under your control. If we were starting fresh, then I might have done things differently, but these predefined subnets that AWS has already created, for some reason they're in a strange order, but our zone C has the addresses 172.31.0 through to 15. And then 16 through to 31 are the addresses for zone A. And then the addresses, and it will be from 32 up to, I think, 47 are for zone B. I can verify that in the calculator. I'm going to copy in 172.31.32.0/20. And yes, the last IP in that range is the one ending 47.255. So this is entirely up to me, but as the architect, I'm going to decide then that for the private subnet for zone A, this is going to be all the addresses starting 172.31 and then we're starting from 48.0, and we're going to use a similar sized block of IP addresses. So I'm using /20 and then say, yes, create. Great. So here's our new subnet and confirmation there that there are 4,091 available addresses in that range. And again, if I copy this into the calculator, we're confirming there that the last IP address in this range will be the one with a 63 in the third position. Now that will probably be all I need for this demonstration, but I may as well go on and create the other subnets. So I'll create one that's going to be private for zone B. So not forgetting to set the availability zone. And then this block will be 172.31. The first address will be 64.0 and the same size block as before. That will be 4,091 addresses. Oh, and by the way, as we're creating these, we have not been asked whether we want to auto-assign public IP addresses in this subnet. Well, we don't need to, because can you see here that the default is no, which is exactly what we want for these private subnets. So just one more to go. This is going to be private_C in zone C. And this block will be 172.31. Now I think the last block that we created, the private B, I think its last address will be, I think, 79. But I'm doing that off the top of my head, so we can calculate it. The last block we allocated, 172.31.64.0/20. 172.31.64.0/20. And yes, the last IP in that range has its third number as 79. So the next unused one will be 80.0. Now, helpfully, although this isn't the easiest thing in the world to do, you will get an error if you accidentally overlap any of these blocks. So if I were to say 75.0/20 in here, as soon as I tab away from there, it's saying it overlaps with that existing block. So I really meant to say in there .80.0, and that's looking good. And I can now create that subnet. Okay, so that's done. And there are a lot of different ways that you can slice and dice and allocate these subnets. This is just one example way of working. If you were the chief architect of this system, then these will be the kinds of decisions you need to make. I really only went for the block size of 20 because that's what Amazon had already been using. It actually sounds like quite a big block, but it's kind of a sensible size, really. I can imagine that I might possibly have 1,000 microservices in a few years' time, and 4,000 seems like a kind of a big enough number to allow this system to grow. Anyway, what that means now is that when we launch instances, we can choose whether we want it to go into a private subnet or a public subnet. And the way we do that is by simply modifying the Ansible script. Now, we've never needed to do this so far on the course, but when you launch an EC2 instance using Ansible, there is going to be a parameter in here for, and I had to search for it a little bit. I thought it was going to be called subnet ID, but actually it's called VPC_subnet ID. And all you do is look up in your list here. If we want to launch an instance into the private subnet for availability zone A, then we just take this ID here. So let's do that then. I'm back here in GitHub and I'm already on my deploy.yaml script, and I'll edit it. And we're looking for the EC2 task. So really, this assign public IP is redundant because regardless of what I put onto here, it's not going to have any effect. However, I'm going to leave it in just to remind myself, if I'm a maintenance engineer or something looking at this script, I can see at a glance that this EC2 instance is going to be a private instance. But what we need now is the VPC_subnet_ID. And it really doesn't matter which of the zones we launch into, as long as it's one of the private ones. So I'll go for private A and copy that in. And that's it. Let's do a commit. And before I go back into Jenkins, I'll switch back across to the EC2 console. And earlier I terminated the position tracker. So let's try to redeploy that again. And I'll do that by running the build. For me, this will be build 40, and I definitely want to watch the console output for this. Great, we're now at the provision and instance stage, which as usual will take a few moments, but we can, even though that's still running, go to the EC2 console and do a refresh and see what's going on. So I have here an instance in the pending state. It is in availability zone A, which looks good. It's still initializing, however. I can see that there's nothing under the public IP address, and there is a private IP. So that's good, but it might just be that it's still starting up and maybe it hasn't yet got around to allocating an IP address. But actually now I can see that this instance is running and there's no public IP address. You might think we've solved the security problem. However, if I go back to Jenkins, and I have been talking for quite a while now, and yet it is still stuck on waiting for the SSH server to start responding, one of those steps that we have in our Ansible script. Now, this is quite a simple problem, really. You might be able to work out why that's happening. If I go across to the Ansible script, We worked quite hard building this Ansible script on the previous course, but one of the things we did in here was that as we launched instances, we were gathering the public IP addresses of the instances into this variable called EC2 hosts. And in fact, here's the task that's hanging. This is where we're waiting for port 22 to become available. And we're actually using the public underscore IP address. We're actually trying to contact port 22 on the public IP address. Well, of course, those IP addresses don't exist anymore. There's simply nothing there. That's not a big problem because they do have a private IP address. And remember that our Jenkins instance is running in the virtual private cloud, the VPC. So there would be no problem with using the private IP here. It's just that we just need to work out what the variable's called for the private IP address. And if I switch back to that build, which is still hanging, very helpfully, Ansible is reporting back for each instance that's created. This item variable is showing you the key value pairs for each instance. And all you've got to do is poke around in here a little bit, and you can see there is a variable called private underscore IP, which for this instance would have been one of those 172 addresses. Notice for public IP, we have a value of none. So all that means is, first of all, I may as well terminate this instance. It's never going to succeed. And then back into GitHub, and we'll edit the script. So it's really just a case of changing public IP to private underscore IP on, for me, line 58 and line 64. So that's good. So I am relying on the fact here that the Jenkins instance is running in the same VPC as the system itself. I think that's a reasonable assumption, but I guess that could cause problems on some projects. It's certainly okay for us. So by now the script has failed, so we can go back to the project and run the build again. This is going to be build 41, and as before, the provision and instance stage takes a while, but it's gone through now. So we're on the SSH task. We have a private IP address here ending in 114. We have quite a nervous wait here because I'm hoping that the SSH server is just taking a while to start up, but there it is. It's now continuing through the script. So we've now reached the task of upgrading all of the packages. Now, I'm going to talk for a few moments while that's running. In the AWS console, it's worth checking again. Here's our new position tracker. It doesn't have a public IP address. It looks like all is well. However, and I have done an edit off camera, I'm coming back into the Ansible script. Oh dear, it looks like the playbook execution has failed. And it was actually the upgrading all of the packages on the instance. It says it's failed. It's a very confusing error. It's saying that another app is currently holding the yum lock. Now we're using yum to upgrade all of the packages on the instance. So it looks like there's something wrong with yum. Now I don't think just by looking at this error, you could work out what's going wrong. It's actually quite a significant and serious problem. And that's why I'm going to leave the problem as a cliffhanger. We're going to revisit this problem in the next chapter when we look at what a NAT instance is and why you need one. And, well, I can tell you that once we have a NAT instance correctly configured, this problem will go away. But all will be revealed in the next chapter.